Welcome to the video lecture for section 5.1. This is for STA 2023. My name is Jorge Young, and so in this section we're going to do probability distributions. So we're going to go ahead and introduce the concept of the random variable. We're also going to talk about probability distribution. We're going to also create a graph or a probability histogram that's derived from a probability distribution. We're also going to find the parameters, the mean, the standard deviation, and the variance for a probability distribution. And then we're going to go ahead and do expected value. And so the first thing is a random variable is simply a variable, and it's typically represented by x that has a single numerical value determined by chance for each outcome of a procedure. And a probability distribution is a description that gives the probability of each value of the random variable. It's often expressed in the format of a table, a formula, or a graph. So a discrete random variable is simply a collection of values that are finite or countable. And if you remember back when we talked about qualitative and quantitative, so quantitative variable can be discrete or continuous. Discrete is countable, continuous is you measure. And so if there are infinitely many values, the number of values is countable if it's possible to count them individually, such as the number of tosses of a coin before getting heads. A continuous random variable has infinitely many values, and the collection of values is not countable. So there are some requirements in order to have a probability distribution. The first one is that there is a numerical, not categorical, random variable x, and its number of values are associated with corresponding probabilities. Also, the summation of p of x has to equal 1, where x assumes all possible values. So sometimes the sum does not equal exactly 1, but since we use technology, it should equal 1, so we don't really have to worry about the rounding errors. And then the last one is that every individual value of the random variable x has to be between 0 and 1. And so if we can't get a negative, we can't get anything above 1. And so when we sum up all of the possible outcomes in the sample space, that probability has to equal 1. The summation of the probability has to equal 1. So here's an example of coin toss. So let's consider tossing two coins with the following random variable. So x is the number of heads when two coins are tossed. So the above x is a random variable because its numerical value depends on chance. And so the possibilities would be 0, 1, or 2. The probability of getting 0 is 0.25. The probability of getting 1 is 0.5. And the probability of getting 2 is 0.25. And if we add those together, we get 1. The variable x is also numerical, 0, 1, and 2. And then each value of p of x is between 0 and 1. Now, the random variable x in the table is a discrete random variable because it has three possible values, 0, 1, and 2. And 3 is a finite number, so it satisfies the requirement of being finite. Now, the next thing we're going to talk about is a probability histogram, which is similar to a relative frequency histogram, but the vertical scale shows probabilities instead of relative frequencies that are based on the actual sample results. So here's the probability histogram for the number of heads when two coins are tossed. Now, another way to demonstrate a probability distribution is using a probability formula. And a probability distribution can also be a formula. So we have this formula. P of x is equal to 1 over 2 times 2 minus x factorial times x factorial, where x can be either 0, 1, or 2. Now we find that P of 0 using this formula is 0.25, P of 1 is 0.5, and P of 2 is 0.25. And these are the same probabilities that we found previously. Now here's an example that shows you a mistake in a probability distribution. So hiring managers were asked to identify the biggest mistakes that job applicants make during an interview, and the table below is based on their responses. And so the table below describes a probability distribution. So we can see x, and we can see p of x, and then the total. So the table violates the first requirement because x is not a numerical random variable. So the values of x are categorical and not numbers. The table also violates the second requirement because the sum of the probabilities is 1.57, where it should be 1. So because the three requirements are not satisfied, we conclude that the table does not describe a probability distribution. Now remember that with a probability distribution, we have the description of a population instead of a sample. So the values of the mean, standard deviation, and variance are parameters and not statistics. So quickly to review, statistics derive from samples and parameters from the population. So the mean, variance, and standard deviation of a discrete probability distribution can be found using the following formulas. So the mean, mu, for the probability distribution is the summation of x times p of x. So it's the sum of the product of x times the probability of that particular outcome. The variance, sigma squared, for a probability distribution. There are two formulas. I prefer to use the third one, which is the summation of x squared times p of x minus mu squared. And then the standard deviation sigma is simply the square root of the variance. Now, expected value. The expected value of a discrete random variable x is denoted by e and its mean value of the outcome. So e is equal to mu, and e can also be found by evaluating the summation of x times p of x. So here we're going to go ahead and find the mean and the variance and the standard deviation. So the table describes a probability distribution for the number of heads when two coins are tossed. We're going to find the mean, the variance, and the standard deviation for the probability distribution described. So here we can see x, p of x, x times p of x, and then this notation just simply means that we took the values that we got here in this column and added them up. And then of course here they used the second formula, which is x minus mu squared times p of x, and then they got this value here, which is the variance. So the two columns on the left describe the probability distribution, and then the two columns on the right, for the purposes of the calculation required, will give us the expected value and the variance. And so in this case, the mean is 1 and the variance is 0.5. So the standard deviation is the square root of the variance, so the standard deviation sigma is simply the square root of 0.5, which rounds to about 0.7 or 0.71. So when tossing two coins, the mean number of heads is 1, the variance is 0.5, and the standard deviation is 0.7. Also, the expected value for the number of heads when two coins are tossed is 1 head, which is the same value as the mean. If we were to collect data on a large number of trials with two coins tossed in each trial, we will expect to get a mean of 1. So the publisher talks about significantly low and high values. This is pretty much the standard. It's plus a mu plus or minus 2 sigma. Anything above or below is either high or low. So the question is, we found that when tossing two coins, the mean number of heads, mu, is 1, and the standard deviation is 0.7. So use those results and the range rule of thumb to determine whether two heads is a significantly high number of heads. So here you can see that mu plus 2 sigma is actually 2.4, so any values above 2.4 will be significantly high. But of course, if we get 2, which is the most that we can get, it's not going to be significantly high. Next thing is expected value. So the expected value of a random variable x is equal to the mean mu. We can therefore find the expected value by computing the summation of x times p of x, just as we do for finding the value of mu. So the first example that I'm going to do is playing a card game with $0 to play. And so you don't have to pay anything to play. You choose a red card, you win nothing. You choose a spade, you win $3. You choose a club, you win $5, and you choose the ace of clubs, you get $15. So let's go to Excel so we can see what that looks like. So here's the information that we got. You get a red card, you win nothing. Spade, you win $3. The club, you win 5, and the ace of clubs, you win 15. So the probability of getting a red card, there are 4 suits, so the probability of getting a red card would be 1/2. So that would be 26 divided by 52. And then the probability of getting a spade, since there are 4 suits and spades is one of them, would be 13 out of 52. And then clubs would be also 13 out of 52. And then the ace of clubs would be 1 divided by 52. But the issue here is that in order to calculate these last two, the club and ace of clubs, we have to use the formula that we were introduced previously. So here we're looking for the probability of a club or an ace. So then we have to find the probability of a club plus the probability of an ace minus the probability of the ace of clubs, or ace and club. And so we have to subtract it from one of these. We can't subtract it from the ace of clubs. So this one, instead of being 13 out of 52, it's going to be 12 out of 52. And then so now we're going to see if it fits the criteria for a probability distribution. X, all numerical. P of x adds up to 1. And so it meets all the requirements of a probability distribution, and the fact that all of the probabilities are between 0 and 1. Now, This sum down here will be our mean or expected value. So if we were to play this game, what is the expected winnings? So the first thing that we're going to do is we're going to do x times p of x. And then simply I'm just going to go ahead and drag this so I don't have to do it multiple times. And I get a expected value of $2.19. So what does that tell me? In the context of the game, since I'm not paying anything to play, and if I were to play this game, randomly I'm expected to win $2.19. That doesn't mean I'm always going to win $2.19, but I can't lose any money. So therefore, it would be a good game for me to play. The next thing we're going to calculate is the variance and the standard deviation. So the first thing that we have to do is we have to square our x. And so I'm just going to go ahead and square the x in this column. Once I get that, I'm just going to go ahead and drag it. And then the next thing that I'm going to do is in this column, I'm just going to multiply x squared times the probability. And I already did that. And then I'm going to sum up that column, which is this value right here, which is 12.34. And then what I'm going to do is I'm going to use the formula. And the formula that we're going to use is simply the value, the sum of this column, minus the expected value, or mu squared. And then we take the square root of that value, and we get 2.75. So here we got the variance and the standard deviation for playing this game with $0 to play. Now let's get back to the next example. Well, what happens if I have to pay $2 to play? So everything is still the same. I pay $2 to play. I win 0 if I get a red card. I get $3 if I get a spade. I win 5 if I get a club, and I get 15 if I get the ace of clubs. And so going back here, this is so I paid $2 to play. If I get a red card, I get 0, so I lose my $2. For a spade, it says I win $3, but since I paid 2, I only win $1 if I were to win. For the club, it said $5, but since I paid 2, I only win 3. And then this one is $15, but I paid 2, so it's only 13. The probabilities remain the same, so that doesn't change. Just go ahead and type in these in here real quick. And then of course here I'm just going to go ahead and complete the table. So this is going to give me my expected winnings if I were to play this game. And my expected winnings is 19 cents. So although I'm paying $2 to play the game, I'm expected to win 19 cents on any random game that I play. So the expected winnings is still positive. And so here, to complete this table, I'm not going to complete this table in this example. We'll go ahead and do that in class. But if I were, all I had to do was just fill this in with x squared. And then this is going to fill in by itself. And then I get the variance and the standard deviation. And I also can do the same thing if I were to pay $3 instead of 2. Again, red it's $0, so I lose 3. Spade, it says I win $3, but I paid 3, so that's going to be a 0. Club says I win 5, but I paid 3, so I only win 2 if I get a club. And then this one will be 12 since I paid 3. And again, the probability will be exactly the same, so that doesn't change. Let me get these in here real quick. And then we can go ahead and find the expected value. So not paying anything is good. Paying $2, I'm still winning money. But then here I find out that if I have to pay $3, and in this game means I'm going to lose money. So I don't want to actually play this game paying $3 because I'm going to lose on average 81 cents per hand. And let's go back to this. And that is the end of 5.1. Thank you.